Hi everyone, today we are going to talk about parametric equations. So parametric equations, we're going to take a step away from our normal two-variable equations, and we're going to find a way to involve a third variable. So we're going to do this in a way where we're not going to be graphing anything three-dimensional, but we're going to see if there's a way that we can write x and y in terms of another variable. So imagine a scenario where you have a quadratic equation that represents horizontal and vertical movement of a projectile. It's sometimes very useful to know just the horizontal and just the vertical, but sometimes it would also be nice to know when the object is at each location. So in that case, it'd be really nice if we could write everything in terms of time. So that third variable that we're going to introduce is called the parameter. So once again, we're going to write x and y as functions of our parameter. And this is going to give us a graph that we call a plane curve. So to find a plane curve or to graph a plane curve, there's a few different ways to do it. One way is literally creating a t-chart, and we could fill in our x and y values by using the two functions that we are given for x and y. So for parametric equations, you do need to be given an equation for x and an equation for y, but notice that they are both in terms of our parameter, which in this case is t. So let's give one of these a try. Here we are given our two parametric equations. Both x and y are functions of t, and we're also given a restricted interval for t. So to do this, or one way you can graph this is, like I said, a simple t-chart. So we're going to be plugging in the values -2, -1, 0, 1, 2, and 3, which is our interval for time, or t. We don't exactly know what t represents here. And we're going to substitute it here to find all of our x values and here to find all of our y values. And then we're just going to plot the x, y coordinates as we would any other graph. So let's start by plugging in all of our t values into our x function. So here we would have 0, here we have -3, -4, -3, 0, and 5. And then we can plug all of our t values into our y function to find our y values. So here we have -1, -1/2, 0, 1/2, 1, and 3/2. So we are going to plot these points. Okay. So we have a point at 0, -1, -3, -1/2, -4, 0, -3, +1/2, 0, 1, and 5, 3/2. And we connect our dots. But now here's another very important aspect of parametric equations. They have an orientation. So this orientation is essentially telling us how is our graph, or how is our object moving? Is it going to be traveling like this? Or is it going to be traveling like this? And clearly we started here and we plotted our points going in this direction. So to show the orientation, we're actually going to add on little arrows onto our graph to show the movement of our object. So all of our parametric equations should have these little arrows, and it will represent the movement. All right, go ahead and pause the video and give this one a try. Okay, so here I made a little t-chart again. Notice that I changed the scale of my y-axis, but we know that this first, the far left side of our interval started over here. The far right side of our interval, or the end of our interval, was here. So that's how we know that our graph should be moving in this direction. All right, so now we're going to talk about a different way to graph parametric equations, and we can actually do this by eliminating the parameter and rewriting our parametric equations as a rectangular equation, which is just an equation with just x and y. So the way you do it is pretty straightforward. You pick one of your parametric equations and isolate the parameter. So we could solve for t, and then you substitute that into the other equation, and then you see what you have. So this is your rectangular equation, and oftentimes it will make one of our conic sections. So we put it in standard form and we graph it. Now these can get a little bit tricky because we have to consider the domain of our original equations, and we also have to consider the t values that we're working with, but we are always going to need to keep in mind what our original equations were. We can also use our original equations to help us find the orientation of our graph. All right, so let's start with this problem. So here we're given our functions for x and y. They want us to eliminate the parameter, and we're going to sketch a graph. So remember, to do this, we pick one of them and we isolate our parameter. So I'm going to pick our x function, and I'm going to solve for t. So I'm going to square both sides, and then I'm going to multiply by t plus 1 and divide by x squared. And then in one more step, I have isolated t. So I'm going to take that and I'm going to substitute it into our other equation. So we have 1 over x squared minus 1 over 1 over x squared minus 1 plus 1. So those are going to cancel out. And then I can simplify this by either multiplying by the reciprocal of our denominator, or just by multiplying the numerator and the denominator by x squared. And I'm left with x squared, 1 minus x squared over 1. So you can see here that it looks like we should just have a downward facing parabola that has a vertex at 0, 1. However, we have to go back and check our original parametric equations to see what's going on with our domain. So let's consider this equation. So I can tell a lot from this. First of all, I know that there's going to be a restriction on t for two reasons. One, you can't have 0 in the denominator, so this value can't be 0, and also you can't take the square root of a negative, so the value inside our radical must be positive. So usually for radicals, we say the radicand, the inside, must be greater than or equal to 0, but in this case it cannot be equal to 0, so we'll say t plus 1 must be greater than 0. So t must be greater than negative 1. And let's consider the entire function, because this represents our domain. It's our x value. So if you look at what we have 1 divided by the square root of something. I know for a fact that there's no way that this denominator is going to be negative. So I know that this value can never become negative, and I also know that this value can never become 0, which implies that x must be positive. So when I'm graphing this downward facing parabola, I'm going to use the domain restriction that x must be greater than 0. So let's do that. So I have a vertex at 0, 1, although I don't actually have 0, 1 included in my graph, and then I just have a downward facing parabola. So this is just a really rough sketch. And actually I don't want to include an arrow on that because we actually need to now find the orientation of our graph. So here, the way you can find if our particle is moving this way or this way is by testing a couple of t values. So I'm going to test the t values using our y function. So we know that y is t over t plus 1. So let's say t equals 1, or let's say t equals 0. If t is equal to 0, then I know that y is equal to 0. So I know that my coordinate is somewhere around here. This is what's happening when t equals 1. Now let's test when t equals 2. When t equals 2, my value is 2 over 3, which is above the x-axis. So it's somewhere up here. So I can see that as my interval progresses, I'm actually moving in this direction. So the orientation of our graph looks like this. So once again, you can just try testing 2 consecutive values to see if your values are moving in this direction or down in this direction. And in this case, we could have plugged it into x or y. I chose to plug it into y just because it seemed easier to simplify. All right, go ahead and pause the video and give this one a try. Okay, so let's first check the equation. So here, when you substitute into the second parametric equation, you should end up with y equals 1 plus 2x squared. So we have a positive parabola with a vertex at 0, 1. From our original parametric equations, we can tell that x must be positive. It will never be 0. It will never be negative, which means that we have a domain restriction for our graph. And so that's why I plotted it like this. Notice we don't include this part of our parabola. I also should have an open circle here. Now, if you test a few of your t values here, if I plug in t equals 2 to y, I have y equals 2. Now, if I plug in t equals 3, we get y equals 3 halves. So you can see that our y values are actually decreasing as t increases, which implies that the orientation of our graph is moving towards the y-axis. All right, so now we're going to try some that have a different parameter. Here you can see that our parameter is our angle. So imagine like a scenario where you have the minute hand on your clock. You can figure out what the horizontal and vertical distance of some point on your minute hand is for any angle within your clock. So that could be an application of having theta as a parameter. But we're going to try to start this in the same way. Usually we would say isolate the parameter. However, that's going to be a little tricky to do because we don't want to work in arc cosine or arc sine, but let's isolate it as much as we can. So let's say the cosine of theta is x over 3, and the sine of theta is y over 4. Now, if we want to write a rectangular equation with just x and y, I'm wondering if there's some equation that we can create that uses just cosine and sine. And if you think way, way back to when we first learned trig, there is a nice trig identity that we can use. We know that cosine squared plus sine squared should always equal 1. Well, if I know that cosine squared is x over 3, and I know that sine squared is y over 4, I can substitute those values, and now I have a rectangular equation. In fact, I actually have an ellipse, and it's already in standard form. So here you can see that we have a vertical ellipse. So we're going to graph this, and then we're going to look back at our interval to see what direction our graph is moving. So here our center is going to be at 0, 0. I know it's going to move 4 units up, 4 units down, 3 units to the right, and 3 units to the left. So I have an ellipse that looks something like this. But now I need to figure out the orientation. So to do that, I'm going to look at our interval for theta, and I'm going to start plugging in some points. So let's start when theta is 0. Well, if theta is 0, if I plug that into my x function, I know that the cosine of theta, or the cosine of 0 is 1. So x equals 3 times 1, so x is 3. The only point on my graph where x equals 3 is right here. So I know that this must be the point where theta is 0. But now I need to figure out, okay, is my object moving this way or this way? And so the next thing I'm going to want to find is a y value, because if I find another x value, let's say I find that x is 1, I don't know if that goes to this point here or this point here. So I want to essentially know, is my graph moving up or down? So I'm going to pick another value for theta, and I'm going to plug it into y. So let's pick the point theta is pi over 2, because that's a really nice value for sine. I know that the sine of pi over 2 is 1, so 4 times 1 is 4. So y would equal 4. And the only point on my graph where y is 4 is right here at the top. So this occurs when theta is pi over 2. So I can tell that my graph is moving in this direction. So that's the orientation of the graph. So you simply need to go back and test a few of your points, but just pick wisely. Because there's definite values for theta that make it really easy to evaluate cosine and sine. And also you want to make sure that you're evaluating for the correct variable. Once again, if we had picked a value for x, we don't know if x goes here or here. So you want to make sure you can figure out what direction it's actually moving. All right, we're going to try one more problem together. This one we're working with secant and tangent, and we have a different interval for theta. So right off the bat, before we do anything else, I want us to kind of interpret what's happening for this quadrant. So we know that this is quadrant 2 to quadrant 3. So if I look at my values, I know that tangent is positive in it's negative in quadrant 2 and positive in quadrant 3. So it could be really anything. But if I look at this value, I know that secant is the reciprocal function of cosine. And I know that cosine is always negative in both quadrant 2 and quadrant 3, which means that secant is always negative in quadrant 2 and quadrant 3, which implies that our x value is going to be negative. So I can just tell right off the bat that I do have this domain restriction. I know that because secant is always negative in these two quadrants, I know that my x value is going to be negative for my graph, despite what my rectangular graph might look like. So now let's go through that same process of isolating secant and tangent. We're going to isolate theta as much as we can. So we have secant of theta equals x minus 1 over 3, and we have tangent of theta equals y plus 3. So we want to find a way to rewrite just using x and y. So I'm wondering, is there some sort of equation or identity we know that involves just secant and tangent? And there is. We know that 1 plus tangent squared theta equals secant squared theta. And I'm going to rewrite that to say secant squared theta minus tangent squared theta equals 1, just because I'm anticipating maybe having some type of conic section, and I know that the standard form will always have our equation equal to 1. So let's substitute what we know. If I take the secant value and I square it, I have x minus 1 squared over 9 minus y plus 3 squared, and I'll say over 1 equals 1. So I can see here that I have a horizontal hyperbola. So I have a hyperbola that is horizontal. So remember, we're going to get a shape that looks like this. However, we know that our x value should be negative due to our quadrants and the functions that are used. So we're really going to probably be focusing on this portion of our graph. So let's start graphing. So I know that this parabola has a center at 1, -3, although that's not actually part of our graph. And I know that my a value is 3, so I'm going to move to the right 3, although we're not even going to bother on this side because we know that x should be negative. And then we're going to move to the left 3 to find our vertex, our other vertex that we're actually going to use. So we're going to have a vertex right here, and our graph is going to look something like this. So now all we have to do is figure out, well, what is the orientation of our graph? Is our object moving like this, or is our object moving like this? And so we're going to need to go and test some values for theta. However, we want to make sure we're plugging it into the correct equation. In this case, it's not going to be very useful for us to substitute into our x, because for each x value, there's 2 y values, so we don't know which one. So we're definitely going to want to know what our y values are. We want to know if our graph is essentially moving up or moving down. So I'm going to pick some values for theta, and I'm going to plug them in to our y function. So I'm going to rewrite this here so we can know what we're plugging it into. Okay, let's pick some nice points because, well, we know that there's some nice points for tangent. We know that tangent is equal to positive or negative 1 when the reference angle is pi over 4. So let's use the value 3 pi over 4 because that's within, that's a value in quadrant 2, so it's within our interval. So I know that the tangent of 3 pi over 4 is -1, so I know that that means y is going to be -4. So that's going to be some value down here. This is when theta is 3 pi over 4. Now let's test another value. Let's test what's happening when theta is 5 pi over 4, which is in quadrant 3. So tangent of 5 pi over 4 is positive 1. So negative 3 plus 1 is negative 2. So y equals negative 2. So I can see that our graph is actually going up. This is what's happening when theta is 5 pi over 4. So as my interval progresses, I can see that my graph is actually moving with this orientation. So by testing a few nice angles, and by nice I mean angles that work really well with tangent, I can tell that my graph is slowly moving up, so is therefore moving in this direction. All right, go ahead and pause the video and give these two problems a try. All right, so for our first one, if you make this substitution for cosine and sine into one of our Pythagorean identities, we end up with x squared over 25 plus y squared over 9 equals 1, which is a horizontal ellipse. If you test the points theta equals 0, you'll see that that gives us an x value of 5. The only time that occurs is here. If you test theta equals pi over 2, you get a y value of 3. Because the sine of pi over 2 is 1, so y would equal 3, and that point must occur here. So I can see that our graph is moving in this direction. For part B, in this case, when I look at our restriction, I can see that in quadrant 2, once again, in quadrant 2 and 3, secant is negative. In this case, that implies that y is negative because the secant function is part of our y function. So I know that our y value is going to be negative. This is going to be useful because if you simplify these values, you can see that we actually have a horizontal or a vertical hyperbola. So we need to know, should we focus on the top part or the bottom part? And since y should be negative, we're going to focus on this bottom part. So our hyperbola has a center at -1, 2. Our a value is 2, so I moved down 2, and that's my vertex. So I know that I have something that looks like this. And I tested 2 points. When theta is 3 pi over 4, I plug that into our x value. X is -2. And when theta is 5 pi over 4, x is 0. So I can see that my graph is moving in this direction. All right, the last thing we're going to do is we're kind of going to do the reverse of what we've been doing. We're going to take a rectangular equation and we're going to write it as a set of 2 parametric equations. So we're going to do 2 different cases, but both for y equals 1 minus x squared. So let's focus on this first one. We know that y equals 1 minus x squared. And for part A, they tell us that x is going to be t. So that's part of our parameter. So then I am essentially just going to take that and plug it in here, and that allows me to write y in terms of t. So y equals 1 minus t squared. And this is my set of parametric equations because x is written in terms of t and y is also written in terms of t. So it's pretty straightforward. For our b, we start with this same rectangular, except we have a different relationship for our x value. If I look at this and I solve for x, I can see that x is going to equal negative t plus 1. It's going to equal negative t plus 1. So if I go back and plug that into our formula, we can see that y equals 1 minus negative t plus 1 squared. And if we simplify this, we get y equals, we'll say 2t minus t squared, or you could say negative t squared plus 2t. But either way, we have our 2 parametric equations. We have x written in terms of t, and we have y written in terms of t. All right, go ahead and pause the video and give this last one a try. Okay, for part A, we already have x in terms of t. You substitute it, and then we have y in terms of t. Y equals t squared plus 2. For the second one, solve for x. So we have x in terms of t, substitute that x value in, and then you have y in terms of t. So these two equations are the parametric equations. All right, that is all for today's lesson. Thank you so much for watching.